Hello, my name is Destiny Black,
And my name is Zoe Rodriguez.
and this is the surrogate optimization for supercritical fluid extraction coupled with supercritical fluid chromatography. In the executive summary, we have the advancement of separation scientists that can provide insight and knowledge for both concentrations in chemistry and in engineering. Supercritical fluid extraction is a flexible extraction process that can remove chemical components, and it can be coupled with offline SFC, which is supercritical fluid chromatography. The research integrates statistics and optimization research to establish an effective method strategy for the development of online SFE SFC analysis. The research concluded that methodology integration with analytical chemistry results in an effective exploration of mass spectrometry parameter space. The SFE SFC background shows that it is an all-in-one analytical strategy which reduces error and increases efficiency, utilizing the benefit of supercritical fluid to aid in extraction and separation. Figure 1 shows the general outline of the instrumentation used. Beginning with 1 through 12, it uses SFC, SFE, and mass spec to analyze the compounds chosen for this experiment. Specifically, SFE consists of two main modes, static mode and dynamic mode. In Figure 2, Section A, it shows static mode, which is the marination of the product with CO2 in supercritical state, along with the modifier of choice. Dynamic mode is the opposite. It changes the direction of flow, so it heads towards SFC, and pumps fresh CO2 in the supercritical state towards the column.
Going into the framework and setting of surrogate optimization, for the framework, we will be referencing Figure 3. Figure 3, starting with input space X. Our input space X includes sample material in the research, which was silica, as well as target analytes, which are diazepam and isovanillin. Decision space Y in the research includes variable parameters of the SFE, SFC, MS instrumentation, including extraction pressure, static time, dynamic time, concentration percentage, and flow rate. Lastly, outcome space C includes extraction performance metrics like chromatographic efficiency. Task 1 includes the design of experiments, and Task 2 includes efficient surrogate optimization. Surrogate optimization is a technique that uses metamodels or surrogate models to optimize the response surface, and for this we will be referencing Figure 4. The initialization in our surrogate model is the Latin hypercube design. Latin hypercube design is a space filling technique that is based on Latin hypercube sampling, which takes a single sample from each row and column of a hypercube containing more than 3 dimensions. These samples are random and they disperse in a probabilistic sense. The responsive variable from the SFE SFC experimentation is chromatographic efficiency, which will be later explained by Destiny. The model being used in our circuit optimization is tree-knot multivariate adaptive regression spines, or TK-MARS for short. MARS is useful in its feature selection ability and its robustness towards uncertainty. Tree-knot MARS is able to identify peaks and valleys where potential optimum solutions lie and improves the flexibility of MARS, as well as adds promising candidate points to our dataset. Exploration and selection portion of the surrogate optimization is used in the form of sorted exploration exploitation Pareto approach, or sorted EPA for short, and sorted EPA is outlined in Figure 5 more detailed. The stopping criteria utilized in our surrogate optimization was 9 evaluations due to time constraint and experimentation complexity.
Looking at the experimental background, the two analytes chosen are diazepam and isovanillin, with the compound of interest specifically being diazepam. Denoted below are the pKa values, which shows acid strength, and the log P values, which shows how hydrophilic or hydrophobic the compounds are. As you can see, both numbers are drastically different from each other, and allows us to compare two different compounds and see how they work in the circuit optimization. As stated above, we are looking at column efficiency, which is calculated by dividing peak area by peak width, and it measures the column's ability to separate analytes successfully. Vessel packing materials were silica and Shimachu dry rite. Looking at the experimental setup, in Figure 6, it shows the vessel preparation, and the vessels what is used in SFE. Each was packed with 1 gram, 0.5 grams being the silica and 0.5 being the Shimachu dry rite, and was spiked for 100 microliters total volume, 50 being the isovanillin at 10 ppm, and the other 50 microliters being diazepam at 1 ppm. The column used is a Restec Raptor silica column, and the modifier was methanol, with the additive being the 10 millimole of ammonium acetate. The ionization source is ESI in both positive and negative mode, each for its own compound, and the mass spec mode being MRF.
Going into the experimental results sections, runs 1 through 6 were generated based on maximum and minimum of each respective parameter's bounds. The results are used to generate the parameter settings for runs 7 through 9. Chromatographic efficiency is plotted in Figure 6. and shows a variety of values that explore the mass spectrometry space. It is important to note that isovanillin was not used in the surrogate optimization and was only used to observe changes alongside the analyte of interest. Going into the conclusions, this research demonstrates the ability to integrate surrogate optimizations with analytical lab experiments. Additionally, the exploration of the mass spectrometry parameter space was successful with a variety of different explored points. Future work will integrate the exploitation portion of surrogate optimization as well integrate the surrogate optimization of multiple chemical analytes. Lastly, on the chemical side, isovanillin requires a higher concentration to produce a strong peak signal.
Thank you so much and have a good day.